Imagine standing on a glowing surfboard 20,000 kilometers above Earth, riding invisible waves of solar wind. You brace yourself as charged particles streak by at 400 kilometers per second. This isn't science fiction. This is our thought experiment in action. We strap a massive magnetic cell to a rigid board. The cell spans a kilometer across, woven from superconducting wires shielded by liquid helium. As the sun spits out electrons and protons, they slant into the magnetic field. The Lorentz force kicks in, bending the path and pushing us forward, just like a water wave pushes a sea surf. First, we pick the best spot, the Sun-Earth Lagrange point L1. Here, gravity from Earth and the Sun balance. Our board floats without constant drag. We unfold the sail and activate superconducting coils. The magnetic bubble expands, deflecting solar wind around it. The pressure is tiny, a few micropascals, but over a vast area it adds up. Each second, a minuscule push accelerates our board. With enough time, we reach a comfortable surfing speed of tens of meters per second. We learn to steer by tilting the sail and adjusting current flows. If we angle the magnetic field slightly off-center, we turn the flow of charged particles, generating a sideways force. It's like carving on a wave. Every shift of current is a subtle dance, responding to gusts from solar flares. When a coronal mass ejection arrives, we brace ourselves. The increased particle density and speed double our push. We can either ride the storm or angle away to avoid a violent spin. Energy isn't wasted. As particles spiral along magnetic field lines, they induce electric currents in our superconducting coils. We harvest this energy to power onboard systems, sensors, stabilizers, and even a small greenhouse for radiation-hardened microbes. That fungus glows faintly under ultraviolet lamps, a living indicator of cosmic radiation levels. To stay upright, we use gyroscopic stabilizers. Spinning flywheels counteract sudden tops from uneven particle hits. If a powerful solar flare hits one side of the sail harder, the gyros spin up to keep our board level. Tiny thrusters feed off stored energy to correct drift, but most of the work comes from magnetic feedback loops. The trickiest part is human safety. Solar wind is mostly charged particles, but high-energy protons can damage cells. We wear a suit with embedded magnetic coils, creating a mini magnetosphere around our body. It deflects the worst of the radiation. A layer of liquid hydrogen in the suit absorbs stray particles, turning them into harmless gamma rays, which our suit's lead-lined walls block. As we cruise along, we perform experiments on plasma behavior. We watch magnetic reconnection events in real time. We measure how tiny changes in sail current alter flow patterns. The data could revolutionize space propulsion and radiation shielding. What seems like a wild stunt becomes a laboratory in free space. Finally, we return to L1. Having surfed solar wind for days, we've proven that magnetic cells can not only move cargo, but also carry an intrepid surfer chasing cosmic waves. The dance of particles and fields has taught us new ways to harness the sun's power. Maybe one day, real pioneers will glide above our atmosphere, riding the breath of our star with gleeful abandon.